This is the first lecture in the chapter 13 unit on compounds in aqueous solutions. So we've been looking at solutions. Most of those have been in water, although we've talked about some solutions that occur in other solvents as well. But this chapter will focus exclusively on water-based solutions and their so the first thing we're going to talk about is ionic compounds in water. So remember that ionic compounds involve a metal and a non-metal, and therefore they have charged particles. So you've always got a positively charged particle and a negatively charged particle. When those ions separate from within a compound, it's called dissociation. So the ions come apart and act as individual entities. The number of ions that will form is totally dependent upon the ratio of those ions within the compound. So I'm not sure why my arrows have turned into boxes. That's exciting. So you can see here when these three different chloride-based compounds dissociate, they form some different numbers of ions. So with NaCl, you get just a single Na ion and a single chloride. But with calcium chloride, because calcium has a charge of +2, you get calcium 2+, and you get 2 chloride ions in that dissociation reaction. Aluminum chloride, because it's a 3+ charge, you get an aluminum ion and then 3 chloride ions. So the ratios, again, are dependent upon the charges of each of those ions. If the entire compound dissociates, which is what generally happens with ionic compounds, then you produce for every 1 mole of reactant compound, it will produce 1 mole of so if we're looking at NaCl here, for 1 mole of our Na compound, we will produce a single mole of sodium ions and a single mole of chloride ions. In our second example, we would have a single mole of calcium and 2 moles of chloride. In the third example, 1 mole of aluminum, 3 moles of chloride. So ionic compounds, while they are all made of a metal and a nonmetal, and they all have positive and negative particles, there are quite a few ionic compounds that are not soluble in water. So when they form from a chemical reaction, their density causes them to fall to the bottom of the solution. They're more dense than the water in which the reaction is taking place, and so you see them as a precipitate. When we represent this process, when we look at the movement of ions or the combining of ions within a chemical reaction, we can't represent the ions that don't dissociate. If they are insoluble, then they are therefore bound or combined with some other ion, and so they are not dissociated. There is a table in your book on page 437, and it has about 6 or 7 kind of general rules about how you can predict which ions and compounds will be soluble. There are a few ions and compounds that are universally either soluble or insoluble, but unfortunately far more of them are kind of situation dependent. However, it gives us kind of a general guideline, and we'll be working with it a lot, so it would be a good idea to become comfortable with that table. Some of the things that the solubility table allows us to do is to answer the questions, are known products likely to be soluble? If we know this is what will result from a chemical reaction, how can we predict what that product will look like? And then we can also determine what products are likely to occur. And once we do that, then we can use the solubility to tell us, will that product be aqueous? Will it be solid? Will it be a gas, perhaps? Things like that. So how exactly would we do that? Here's an example of a reaction type, and I apologize, the subscripts got a little crazy here, but we have NH4 so that's ammonium sulfide, plus cadmium nitrate. And we're wondering what are the likely products of this reaction, and will they be soluble or insoluble? So the first thing we need to do is identify our reaction type. In this case, we're dealing with a double replacement reaction, right? We have a compound plus a compound. That leads us to the conclusion that it is most likely a double replacement. There's no oxygen present, so it's not a combustion reaction. It can't be synthesis or decomposition or single replacement. So we're left with double replacement. Then we need to identify the likely products. So if we assume that every part of the compound dissociates into ions, we can show those ions individually, which is what I'm doing here. So we end up with ammonium, which is a positive ion, sulfide, cadmium, and nitrate, which is a polyatomic ion. So if we started with ammonium and sulfide bound together, then those are not going to be in the products because they're already there as a reactant. So then we're going to combine the positive ammonium ion with the other negative, which is nitrate. When we do that, we can see that the charges balance out, right? A positive ammonium and the negative from the nitrate, 1 to 1, so that's a good balance. I'm just going to erase the charges there and scoot this together so it's in a bit of a compound. And then our other compound would be cadmium, which is a 2+, and sulfide, which is a 2-. So again, our charges balance there. So we can erase those, write this as a compound. So we've got ammonium nitrate and cadmium sulfide. Those are the likely products. Then if we look at the solubility table, we can look at the rules. So one of the rules is all nitrates are soluble. So this compound has a nitrate, which means that it is highly likely that it will be soluble since all nitrates are soluble. We get confirmation of that fact when we look at the next rule, all ammonium compounds are soluble. And here's ammonium. So we know that ammonium nitrate is going to be soluble, which means we can add in our state of matter. So it's going to be aqueous, right? It will dissolve in water. And then we can look at our cadmium. When we look at the rules, we find out that most sulfides are insoluble. The fact that it says most usually means that what you'll get is exceptions to the rule listed after the fact. It'll say most sulfides are insoluble. Exceptions include this and that and the other thing. Since there's no exceptions here listed for cadmium, we're going to have to go with what the rule says. Most sulfides are insoluble. So that means that cadmium sulfide will not dissolve in water, and it will therefore form a solid. We can use the information that we've learned about dissociation and the solubility rules to write what's called an ionic equation. The ionic equation is very, very much like a standard chemical equation. The big exception here is that we're representing the ions individually. So we show all of the ions on the left side, just like I did on the previous screen, and then we show all of the ions and insoluble products on the right side. Anything that's soluble gets shown as an individual ion. Anything that's insoluble, which we saw here, cadmium sulfide is insoluble, so we represent it as a compound. There's no individual ions left in the solution after this reaction takes place. What you might have also noticed here is there are some ions, like nitrate and ammonium, that appear on both sides of the reaction. We call those spectator ions because their physical properties don't change. They are ions that are soluble in water on the left and ions that are soluble in water on the right, and so they don't undergo any chemical change of any kind. When we condense overall ionic equation down, we can eliminate anything that is not involving a chemical change. And so what that would look like is this. So nitrate is on the left and it's on the right. Ammonium is on the left and it's on the right. So we're going to get rid of it. The net ionic equation, therefore, would look like this. Cadmium 2 plus sulfide 2 minus yields cadmium sulfide. It just shows the ions that undergo some kind of a chemical change. In this case, they go from being charged particles on the left to being neutral on the right. There is sometimes, we get some instances, and some of the most fun chemistry comes from non-ionic compounds that sort of behave like ionic compounds. These tend to be polar molecules, things like HCl, HI, a whole variety of acids. Water is another one that behaves like it's an ion, even though it's not. Sometimes when we add polar compounds to water, they will form ions in solution, which is really kind of an interesting process. It's called ionization, and it means that the solvent, in this case the water, is forcing a change within that neutral compound. It's forcing the compound to fall apart, to break up, essentially, and form some ions where they wouldn't otherwise do so on their own. We can determine which polar compounds are likely to do that by comparing the bond strength of the two compounds, so the solute and the solvent. If the strength of the attraction, basically if the water or some component of the water is more attractive to the elements involved in the polar compound, then the water will split them up. So basically the water has something that's appealing. Usually it's the electronegativity of one part of the water versus the compound itself. And that attraction will split up the bonds between the compound. Let's look at the next slide and you'll see a picture of this. So down here in this little graphic, you can see hydrochloric acid, where we have a hydrogen and a chloride, and they're sharing electrons. Hydrogen has its 1 and chlorine has its 7. So when they sit closely enough together, it creates a cloud of electrons with a total of 8. So both elements are happy. However, the water comes along, and this highly electronegative oxygen is super attractive to the hydrogen in the partnership in the acid. And so basically the water splits up this hydrogen and this chlorine, and what you get are two ions now all of a sudden. The chlorine gets the extra electron from hydrogen, and the hydrogen's left with nothing. And that makes the hydrogen super, super, super reactive. It has to go somewhere because that lack of an electron makes it very unstable. And so what it almost always does is it latches right onto this water molecule, and it forms a curious little creature called the hydronium ion, where now you have a positively charged extra hydrogen attached to the water. Just a reminder, or kind of a point of emphasis, the halogens, the group 17s, so iodine, fluorine, chlorine, bromine, these guys are the halogens, and they are super strongly attracted to hydrogen-based compounds because they need one more electron, and lo and behold, hydrogen has its 1 electron. And so they always form a polar molecule in that type of a relationship. They also, because that hydrogen's 1 electron is pretty easy to pull away from it, it causes them to be very strong electrolytes. They can pretty easily dissociate into 2 ions, into the hydrogen and the bromide, or any of the other ones. There are some other polar compounds that will form ions, but not very high concentrations of ions, and so we call them weak electrolytes. They do have some charged particles, but not a lot. for the amount of total solute that's present. And then we have, you've seen this one before with sugar. Sugar, no matter what you do to it, the bonds between the sugar molecules are far more attractive and far stronger than any kind of bond that sugar might have with water. And so there's no dissociation at all. There's no ionization happening there. Okay, so that's it for today. Let's have you bring in some clarification questions and write your summary, and we will do a bunch of dissociation and ionic equation writing in class. I'll see you soon.